Hello everyone, I am Linh, a PhD student at Monash University, Malaysia, under the supervision of Dr. Wern-Han, Professor Raphael Phan, and Professor Phung. Today, I will present our paper, Improved Speech Emotion Recognition based on music-related audio features. Here is the structure of this presentation. First, let me introduce about the research problem. In recent years, the search of speech emotion recognition research has shown a high demand for this technology in various applications. If voice technology introduces a better way for humans to communicate with devices, emotion recognition helps improve the human-machine relationship and makes it more natural. In order to achieve that, the emotion recognition model has to be able to run on varying devices with limited computational power. This research aims at designing an efficient model for speech emotion recognition, or SER, for this purpose. The human voice contains information that reflects our inner state, including emotion. To analyze audio data, there are two approaches. The first approach uses handcrafted features, which is the most common method due to its efficiency. Another approach is to utilize deep learning techniques, which requires much more computational resources and training data. As mentioned before, we focused on the most efficient method. Our main research question is it possible to improve the handcrafted feature approach for SER? Let's have a look at the background and motivation for this research. Prior works on the SER domain mostly focused on the speech production-based features which describe how we control our breath, our larynx, and vocal cords. They are called low-level descriptors, or LLD. These features are widely used in many speech recognition tasks, including emotion classification and even COVID detection. The most common LLD features are compare, shemaps, and e-shemaps. These LLD features are highly correlated to arousal or the intensity of the emotional state. However, they perform poorly regarding valence regression, which is how positive or negative. To improve the ability of machines to mimic the human sense of emotions, the model must learn from features that represent a perception of emotional speech. Human hearing ability has a tendency to focus on relative pitch relations or the musical notes. This inspires us to explore features used in music recognition. There are two groups of features. The first group is about pitch-related features. They are often used in automatic music transcription. There are constant Q transform spectrogram describing the absolute pitch spectrum and the chromogram summarizing the energy distribution over 12 musical notes. The second group is about timbre-related features. They help us distinguish two instruments playing the same musical note. Mel spectrogram and MFCC are often used to capture timbre. A sub-research question is how significant are the pitch-related features in emotion detection? With the advancements in deep learning, researchers rely on embeddings, which are extracted from the hidden layers of the deep neural networks. They are often pre-trained on extensive datasets. There are two popular embeddings for audio speech classification, Trill and Wave2Vec2. Trill uses a variant of ResNet to learn representation from the Mel spectrogram. Compared to other embeddings, Trill achieved the highest accuracy for several non-semantic classification tasks, including emotion detection. Wave2Vec2 is the state-of-the-art model for automatic speech recognition. It learns from the raw audio signals with a convolutional transformer-based architecture. Another sub-research question is, how do handcrafted feature sets perform compared to these deep learning embeddings? The following section describes how we designed experiments to evaluate the efficiency of each method. We designed an efficient model for speech emotion recognition by decomposing speech signals into perceptual audio features, just like how our ears encode sound. We then use neural networks to learn representation to classify emotions. We examine several combinations of pitch and timbre features based on the strong connection between music and speech emotion in the human perception of sound. They are called MUSER, which stands for Music-Related Audio Features for Speech Emotion Recognition. There are two main feature sets, MUSER and its extended version, EMUSER. The main feature set contains CQT spectrogram and MFCC, while the extended set includes all four features. The pitch-related features represent the intonation of the voice, for example, high or low, based on our feeling. The timbre-related features represent the color of the voice, for example, warm or cold. According to auditory research, the interaction of these two feature groups is crucial for us to focus on the content when we listen. We also introduced two more variants that use the normalized log power spectrums of the CQT and the MEL spectrogram. The use of log power spectrums is based on the human perception of loudness. Here is the feature extraction process. Each raw audio file is segmented into 128 millisecond chunks by a windowing function. This is the average length of a word. We use Fourier transform and constant Q transform to get the spectrograms and then apply different filter banks and compression to get all the features. Finally, the features are combined and aggregated and ready to be used for the machine learning model. Here is the experimental design. We use PCA for dimensional reduction. The classification model consists of two dense neural network layers with 500 nodes on each layer. We apply 10-fold cross-validation and evaluate on three datasets, RAPTES, CREMA-D, and IE-MOCAP, which are popular datasets for emotion classification. Next, we discuss about the experiment's results. This is the result of the first experiment about feature sets evaluation, and this is the ablation study. Please refer to the paper for more detail. Now I will discuss about findings from these results. There are 5 findings. First, we achieved 86.67% on the RAPTES dataset, which is more than 6% higher than the second best result among acoustic features. It is equal to the deep learning embedding tree despite having a smaller input feature size. Second, the proposed method is efficient in terms of accuracy and model size. According to the aggregated results based on the feature type, the MUSER-based features achieved the highest accuracy. When comparing best result of each type, True still yielded the highest result. However, deep learning-based approach is the most expensive approach since it requires the pre-trained model. The distilled version of True and the classification model still make up more than 90 megabytes of space on disk. Therefore, our method is more effective. Third, the ablation study shows that MFCC gave the highest accuracy on the RAPTES and the IE-MOCAP datasets. Nevertheless, on the CREMA-D dataset, the CQT spectrogram achieved the best result. The main difference between the CREMA-D dataset and the rest is a large number of speakers with different ethnicity. This reveals the effectiveness of the pitch-timbre combination in building a robust SER model. Another finding is about the significance of the pitch-related features. the CQT features surpassed the male features by up to 7% on average. The lowest result from the pitch-related group is of chromogram, since it is the smallest feature. However, its result is still 28% higher than the compared feature, which is the largest set of LLD with more than 6,000 features. These results strongly suggest the significance of the pitch-related features in emotion classification. Lastly, the transformation into a logarithmic representation boosted the CQT and male spectrogram performance by 9 to 14%. With PCA, log CQT spectrogram achieved the best result. This emphasizes the importance of perceptual loudness. We now move to the conclusion part. So far, we have answered the main research question and the two sub-questions through experiments results. By proposing new sets of music-related audio features for emotion classification, we improved the overall performance of the acoustic feature-based approach for the SER task. The results are comparable to the deep learning-based approach while being more efficient. The limitation of this method is the sensitivity towards background noise. Future works include fine-tuning the parameters of the DFT CQT kernels and the filter banks together with the neural networks to hopefully improve the robustness to noise. We also suggest replacing the PCA with other methods such as autoencoders to improve classification results. Finally, we hope that the findings of this research provide insights for us to design better deep learning model architectures for SER. That's it for my presentation. Thank you very much for your attention.